Hi again, welcome back. Let's talk about compound units, shall we? "65 miles per hour is a speed. It describes the speed of something that's traveling fast enough to go 65 miles if it were to travel at that speed for 1 hour. It might not. It might go longer, it might go shorter, it might speed up, might slow down, but if it traveled at that speed without speeding up or slowing down for an hour, it would go 65 miles. 4.5 meters per second is also a speed. Describes something traveling fast enough to travel 4.5 meters every second, assuming it doesn't speed up or slow down. Any speed must have units of some amount of distance per some amount of time. Mathematically, the word per corresponds to division. So we usually say per, but we normally write speeds like this. Okay, what is the dimensionality of a speed? Well, we usually call it speed, but the dimensionality is distance per time. I'm using a tilde here instead of an equal sign because this is not a numerical equality. This is a correspondence. These are dimensionalities. They're not the variables or numbers. Okay. You will often hear physicists say distance per unit time or length per unit time. That just means this is the distance that's traveled per unit of time, where my unit is an hour here or a second here. Speed is a compound dimensionality. That is, it's a combination of fundamental dimensionalities, distance and time. Let's take a look at another compound dimensionality, volume. 15 liters is a volume. Specifically, it's the amount of space that would be taken up by the contents of 15 1-liter bottles. So what is the dimensionality of a volume? Well, a liter is defined to be 1,000 cubic centimeters. That is 1,000 cubes, a centimeter high, by a centimeter wide, by a centimeter deep. All piled together, that amount of space is 1 liter. By the way, when I use a triple equal sign like that, that means is defined to be. It's a stronger statement than happens to be equal to. So with that definition of a liter, I can rewrite my volume as 15,000 cubic centimeters. And that should make it pretty obvious that the dimensionality of volume is length cubed. Any unit of volume, fluid ounces, teaspoons, tablespoons, cups, pints, quarts, gallons, bushels, Olympic swimming pools, must have, if it's a unit of volume, it must have dimensionality of length cubed, whether it looks that way or not, obviously. So the vast majority of units we use in physics or science in general are compound units. In fact, in the SI system of units, which we'll talk about in a few days, there are really only 7 fundamental units. I should say 7 fundamental dimensionalities, each of which has a base unit it's expressed in. They are length or distance in meters, time in seconds, mass in kilograms, electric current in amperes, temperature in kelvins, amount of a substance in moles. You may remember that one from chemistry class. And luminous intensity, basically brightness of light, in candelas. That's it. Any other unit you encounter is some combination of those, a compound unit. Now, part of what makes this tricky is that many common compound units have been given their own name and their own symbol. So just by looking, you can't necessarily tell that they're compound. Some of the more common and more important compound units you might encounter during introductory physics are area in square meters, the volume, which you've met, in cubic meters, speed in meters per second, acceleration in meters per second, which we often write in the more compact but harder to interpret form of meters per second squared. What the heck is a square second? I don't know. We also get density in kilograms per cubic meter. And force in newtons, where a newton is defined to be a kilogram times a meter per second per second. In other words, the dimensionality of force is mass times acceleration, which is mass times distance per time squared. Pressure in pascals, where a pascal is defined to be a newton per square meter of area. Torque, twisting, torque in newton meters. Energy in joules, where a joule is defined to be a newton times a meter. Power in watts, where a watt is defined to be a joule per second. Electric charge in coulombs, where a coulomb is defined to be 1 ampere times 1 second. And electric potential difference, also called voltage, in volts, where a volt is defined to be 1 joule per coulomb. And there are many more. Notice something interesting? Newton meters. That's a little subtlety we'll talk about later. Notice how complicated this can get. Look at potential difference. A volt is a joule per coulomb. A coulomb is an amp times a second. A joule is a newton times a meter. A newton is a kilogram times a meter per second squared. So a volt in terms of base units is really kilogram meters squared per second squared per amp seconds. Kilogram meters squared per amp seconds cubed, if I did that right in my head. So the dimensionality of an electric potential difference is a mass times the length squared divided by a current and also divided by a time cubed. Now, relax. You do not need to memorize all these for this course. But when you encounter a new unit in some physics course you're taking down the road, or even this one, stop and take note. And notice two things. One, what is its dimensionality? It might be a new unit for a dimensionality you already know, or it might be a new dimensionality you haven't dealt with before. And also, how is it defined in terms of other units? And write that down somewhere accessible, maybe inside the cover of your physics notebook. You will want to use that. A common situation is where you are working on a physics problem and you end up with units that don't seem to make sense until you use these relationships to rewrite them in terms of other units, and then things work out. For example, let's say you're doing a problem where you're trying to calculate the power of a motor. And let's say you use some physics ideas and put together some given information and do some algebra, and you end up with 750. And you've been good about carrying your units through, so the units that pop out at the end are 750 Newton meters per second, let's say. Whoa, stop. You're trying to get a power. The dimensionality of power should have units of watts if we're in SI or something like that. What's with this? What did we do wrong? Relax, nothing. A Newton meter is what we defined a joule to be. So I can rewrite this as 750 joules per second. And a joule per second was how we defined the watt. So this is just 750 watts. Exactly as it is supposed to be. Now, let's say you made a mistake in your calculation. Maybe you did the algebra wrong, maybe you grabbed the inappropriate expression or a relationship, or maybe you made an approximation you shouldn't. So you did something wrong and you ended up with the wrong number. Let's say you ended up with a value of 325. Well, if you did what many beginning physics students do, which is to do the calculations with the numbers only, and then just slap units on at the end, you'd say, oh, my power is 325, it's a power, it should be in watts. I'm done, and you would turn that in. And you would never know you'd made a mistake until the grader marked it down, and then you would be sad. But instead, if you were conscientious and carried the units all the way through your calculation, included units with every number you put into it, and canceled the units and moved them and let the units pop out at the end, let's say you might find that the units that came out were Newton meters per second squared. Now that is not obviously more right or more wrong than we had before. But again, you would play the same game. You would say a Newton meter is what we call a joule. So this is a joule per second squared. And a joule per second is what we call a watt. So a joule per second squared is a joule per second. That's a watt per second. And that is not the dimensionality of a power. That's power per time. And you would know you made a mistake. You could stop and go back and find it. In fact, you could track back through your calculation and look and see where your expression went from being dimensionality of power to dimensionality of power per time, and you'd know that was the step where you made a mistake. Easy to find your mistakes. And that's why I say, if you treat units with respect, they will be your best friends. Let's do some work now with compound units.